Good afternoon everyone. Mr. Ish here. Thank you for joining me for today's video. Break away a little bit from our regular topics. And we've been talking about functions and precalculus topics up till now. I want to break away in the terms that I want to present a video which serves as a bridge between precalculus and calculus. And that topic will be the concepts regarding the rate of change, or just a single concept regarding the rate of change. It is actually a very important topic because rate of change has so many applications in so many areas that it is one of those concepts that you might as well spend some time learning. When we're talking about rate of change, why do we have to bother with this whole concept of rate? And here rate does not necessarily imply velocity. Rate of change is something to do with the concept of slope, where you're plotting something against another factor, a dependent or an independent variable, and whatever that plot represents in terms of the curve, and then you're trying to determine how that rate of that curve changes, as you change the variable or as you change the models. That whole concept of rate of change is basically what we're going to be looking at. We have to be also wary about the difference between the average rate of change and the instantaneous rate of change. Again, rate of change here does not specifically mean velocity. You can talk about velocity, but it's not limited only to that. An average rate of change would be based on whatever it is that you're measuring, how that value is affected or changed over a period of time. So you're doing like average values. What actually is more important is the instantaneous rate of change. And we'll be using, of course, a plot or a curve to determine all of this. Instantaneous rate of change is more important because it tells you at a specific point of time how that value has changed. And knowing something at a specific instant of time or point in time is usually more important than knowing it over a period of time, because normally decisions are made based on what you have at hand, right? So having the instantaneous rate of change, the knowledge of that, or how to compute the instantaneous rate of change is more important than knowing the average rate of change. But we look at both of these in this. Again, this is the bridge topic between precalculus and calculus. Next, we should also be worrying about the differences between secants and tangents. A secant and tangent in terms of a graph, I will show you. Secant is to do with the average rate of change. Tangents are to do with instantaneous rate of change. And we're basically determining equations of lines of secants or tangents in terms of a curve I will present you. And that curve can be a hypothetical curve. It doesn't have to specifically model or represent anything. But we'll use that as an example over this video. And also we will redefine or re-examine what the limit is. And I introduced the concept of limits in the video of rational functions and asymptotes. We will look at that concept again. Lastly, here's a little cheat. The cheat is, if you learn derivatives, most of this you can forget about. Not forget about in terms of never have to worry about it, but forget about it in terms of the basic understanding. You can either approach the whole concept of rate of change in two ways. One way, you can learn the whole theory behind it and try to understand explicitly or implicitly what it all means, or you can skip all of that understanding, and in an automatic or robotic manner you can learn the derivatives and do exactly the same thing without getting into the whys behind it. All you will get into is the how you do it, and that'll be it. So that's like a little cheat over here. The derivatives will allow you to skip the theory about all of this and get directly into it. And the derivative techniques are so quick and right to the point, versus some of the technique here I will present you are more long, but then because they're long, you'll actually understand the why behind it. So let's start by erasing this, and we will look at basically secants and tangents first. So here, if you look at our board, I've changed this right up over here a little bit, because we know already we're talking about rates of change, average versus instantaneous. Just for the ability to have more room, I've now put secant versus tangent. Again, I will reiterate, secant is more to do with the average rate of change, versus tangent is to do with the instantaneous rate of change. So just let's look at a very quick plot. Here's a graph, and supposedly, as you might have realized, I like parabolic graphs or functions. If this is right here, a parabolic curve of x squared, if we are to put a specific point on this graph, and let's call this point, if you take it down, it's point x1. And then we know what the y value over here is. The y value is whatever you put in terms of x, and what you get out of it is actually a y value, right? If I'm putting in x1 over here, my y value is exactly f of x1, because when I put this x1 into this, whatever it may be numerically, but your function over here represents what your y value is. Remember, f of x is the same as y, therefore it is representative of what the y value is. And if we extend a few units out over here, and we plot another point on this curve right here, and we call that point x2, okay? And we want to look at the coordinate over here. You know what that will be. It'll be x2, which is your x coordinate. But what will be the y coordinate? It'll actually be f of x2. Why is it f of x2? Because now you're putting the x2 value in your function and solving for that y, and this right here represents your y value. So this is the coordinate pair of these two values, and this is the coordinate pair of the x value. So what exactly is a secant? If you have any 2 points on a curve, right, and you connect them, right, that represents an equation of a line called secant. A secant is a line which goes through your curve at 2 points. And we will say 2 points over here because we're trying to create a distinction between a secant line and a tangent line. But if you were to calculate the slope, of this secant line, right, the slope of the secant line, you'll get an average. It will be basically a representation of an average rate of change. Okay, now I'm going to do abbreviation over here. Rate of change, I'll say ROC, rate of change. So anytime you're dealing with the secant between 2 points, you'll calculate the slope, and we know what the formula of a slope is. A slope is always y2 minus y1 or x2 minus x1. Of course, you have to know what these points are. But if you take a slope of this secant line, the slope, I'm not talking about the equation of the secant line, I'm talking about the slope. The slope of that secant line will represent the average rate of change. I want to bring in these other points. If supposedly we start changing our points over here, and we start creating new other points on the curve, and then we can draw a new secant line, and I'm drawing a secant line only right here to this specific point. I'm changing these other points away because this is the point I'm really more interested in over here. As I start drawing points closer and closer to this, of course I'm changing the direction. This right here is like totally off, but of course I'm changing the direction of the secant line. You see how the secant line was like here, then it's angled here, then it's here, and I draw another point here on the curve, and now all of a sudden my secant line changes in this direction. The point I'm trying to show you, as you bring these x2 values or the values away from your main point closer and closer to the value that you're more interested in, your secant line will change. If the secant line changes, the slope of the line will change, of that secant. If the slope changes, the average rate of change that you are measuring each time with each line will also change. But what would happen if you drew that last point exactly on your original point? Well, you'll have a point on top of the original point, and now you can no longer draw a secant line, because you cannot ideally put one point on top of another and hope to present two separate points, because those points will become coincident, meaning that one point will fall on the original point. When one point falls on the original point, you lose the ability to draw a secant line, but you end up having a tangent line. So let me show you graphically a tangent line, and then that'll bridge what I'm showing you over here with the concept of the tangent line. So let's draw a new graph over here. We'll use the same function, x squared. So here's my f of x function is equal to x squared. Alright, f of x is equal to x squared. Here's a point that I'm interested in right here, and we'll call this x1. And I was showing you previously, if I had a point over here and I start bringing the points closer and closer on this curve, and I put a point, my next point right over here, and I draw a line over here, I'm getting a tangent line. What's a tangent line? A tangent line is a line which grazes your function or your curve at only one point. You see, it's going to point and touch at only one point on this original curve. Here's another example of a tangent line. If supposedly you have a curve which looks something like this, right over here at this point, and I draw a line, that's a tangent line right over here. But if I were to draw one point over here and one point over here and connect these two, now I have a secant. You see the difference between a secant and a tangent? The secant is going between 2 points, and therefore representing a average rate of change. Remember, rate of change will be determined by the slope. Slope will be equal to your rate of change, ROC, rate of change. Alright, that's slope. So the slope of a secant line is representing an average of 2 points, whereas the slope of a tangent line is representing an instantaneous rate of change. And as I said in the very first part of this video, the instantaneous rate of change, which is dependent on a tangent, is more important than the average rate of change, which is derived from a secant line. So how we look at all of this is basically the crux of this video, and I'm going to be showing you that next. So remember the difference between a tangent and a secant. A tangent will graze your curve at only one point, and it will be representative of instantaneous rate of change, a more important slope value for applications. Let's look at it all in another way. If supposedly we have a curve which looks something like this, we have a point over here, and we'll call this point just x. We know the coordinate over here is x comma f of x, because this f of x is representative of your y value. You see this? The f of x is your y value. And I want you to start looking at it in terms of this way now. If we went h units in this direction, of course, you know, if I had 5 over here and I add 5 more to the x value, I ended up with a 10, right? But the amount I added was represented by h. But we have a point over here, x comma h, because we moved h units into the right. You could move in the other direction and do x minus h, but I'm moving in the direction of right, so I'm adding h units. So my new point here is x plus h. Original coordinate was x, my new point is x plus h. But what is the value over here? It will be x plus h, comma, f of x plus h. Why am I putting f of x plus h? Because now in the function, instead of just putting x, which was representative of the original value, our new value is x plus h, so you have to put the whole x plus h into your function to get the y value. The reason why I'm bringing these specific symbols over here is because this is what you might end up seeing in a class or in a textbook, because that's what they commonly show you. So as I told you, if you connect these 2 points over here, you're going to get a secant line. Remember, we're going a little bit back to the concept of secant line, which is average rates of change. If I want to find the slope, I told you the formula of a slope is y2 minus y1 over x2 minus x1. M for slope, symbol for slope. I want to put the equation here for slope. I'm going to look at my y2 value. Here's my y2 value, f of x plus h. What's my y1 value? It's right here, f of x. See, now I'm putting the denominator aspect of the slope formula, which is x2 minus x1. What's my x2 value? It's x plus h, because I moved h units towards the right. It became x plus h. And of course it's x2 minus x1. What's my x1 value? It's x. And you can see we can simplify something over here. So the slope is actually f of x plus h minus f of x, which is representative here of delta y. Remember, change in y over change in x. The x's cancel out and we get here h. If you were supposedly to calculate using values you may actually have, like numerical values, and you put them in here, you will get a slope, but that slope will be representative of your average rate of change. Alright, average ROC. And here's a formula for average ROC, an abbreviation. You put this line on top, it means average rate of change. And this is derived from a secant line. Alright, the secant line plots, or the points on a secant line will give you average rate of change. But what will happen as we bring these points closer in this direction towards x? I showed you what will happen. As you bring these points closer and closer to your original point, you can draw more and more new secant lines. The direction of your secant line will change eventually until the point where you end up with your second point on top of the original point, and you have 2 coincident points, and you'll get that tangent line only. And you will be able to determine the slope of that tangent line and get the instantaneous rate of change. Now the focus over here is how we determine the slope of a tangent line, and there are 2 procedures. One is a long process, which I showed you, which I talked about in my very first part of this video. Remember at the end I had a little cheat using derivatives? Well, there's a process to determining the slope of a tangent line. It depends and it relies on limits. That's a long process, but learning that long process will show you the theory behind all of this. The quick cheat process is just to run the entire function through a derivative and you'll get an answer almost instantaneously. and it'll give you exactly the same result with half or maybe a fraction of the amount of work, but you may not understand the theory behind it. So I want to focus the remainder of this lesson on the concept of tangent lines, because we all know how to do the slopes of secant lines. Is no different than just putting 2 points on any line and determining the delta y over delta x. This right here is your formula for a secant line slope. Just take the change in y values and change in x. Any two values on that point, any two values on a curve which happen to be connected by a secant line, and do delta y over delta x, y2 minus y1 or x2 minus x1, and you'll always get your average rate of change. The more important and difficult aspect is calculating the instantaneous rate of change from a tangent line. And I'm going to spend the rest of this video showing you how to do that. The long way and a very quick way. And the quick way is only just to show you how quick and easy it is. But you may not understand that quick and easy way because we have not yet presented any calculus topics. It'll just be like a preview of what to expect as we start the calculus videos. So let's look at this part of this video. I have a function over here, f of x is equal to square root of x minus 1. And you can see I've drawn only quadrant 1. I eliminated quadrants 2, 3 and 4 from the graph just for the purpose of space conservation. You know the graph of this function will look something like this, starting out at 1, 0 and extending towards infinity. Here my x-intercept is 1, 0. If you put 1 over here, you get root of 0 and you get 1, 0. I have a point on this curve, 5, 2. If you put 5 in place of x, you get 5 minus 1 is 4, square root of 4 is 2, hence 5, 2 is a legitimate point on the curve. With regards to instantaneous rate of change and versus average rate of change, if I were to connect this point and this point which I know 5, 2 with this arbitrary point, and I knew the value of it, and I connect a line between these 2 points, I have a secant line, and you know you can very easily calculate the slope of that secant line because you'll have a legitimate point here, a legitimate point here. You'll do y2 minus y1 divided by x2 minus x1. You'll calculate the slope, and that slope will represent the rate of change for whatever this model represents. It could be maybe the cost of producing something with regards to time. It could be the speed of a vehicle traveling with respect to time. It could be anything, but here we have a hypothetical scenario. Just understand that in this scenario, this model represents something useful, and that usefulness is usually more important when we're looking at tangents and instantaneous rate of change. Remember, instantaneous rate of changes are more important than average because it tells you exactly what is at a specific point of time. Knowing something at a specific point of time is usually more important than knowing something over a period of time. Okay, so that's the whole concept of this video. If I put a point over here, and I'm not going to put any numerical point, I'll just put like we have a value over here, it's x. If I put x over here, what can the y value be? It'll be exactly what you put into your function and you end up getting as your output. Well, it will be exactly root x minus 1, right? Because this is what my f of x represents, right? If I put some number over here, I'll have to solve it out. If I put some number over here and I put it in the function, I'll actually get numerical points. But I'm not using numerical points because I want to show you how we derive an equation of a tangent line. That's how all of these applications appear. You want to determine the equation of a tangent line at a specific point on that curve. The specific point of the curve is given. If you drew a tangent line right here on this point, remember, tangent line grazes the curve at only a specific point. If you determine the equation, you can only do that if you know the slope, and we know the slope over here will represent the instantaneous rate of change. The hard part here is how we determine that instantaneous rate of change, and this is the procedure for doing it. We're going to do it using limits and assumptions. I already have 2 coordinates over here. I have a 5, 2 and I have a x, root of x minus 1. Remember, this is my x value and this is my y value. This y value is represented by the function we're using. F of x is equal to square root of x minus 1. All we have to do is write this whole format in the basic slope equation that we know. It's always y2 minus y1 divided by x2 minus x1. These are my 1 coordinates, these are my 2 coordinates. So the slope will be square root of x minus 1 minus this y1 value, which is a 2, divided by x2, which is represented in here algebraically by this letter x, minus my x1 value, which is 5. This right here is the whole key to this whole process. which is represented by here. What you see over here in just a single letter is represented by this whole equation here. And I have put x over here, change in x, and m. And what does this change of x imply? If this was my x1 coordinate and this is my x2 coordinate, the difference between x2 and x1 is my change in x. And that we'll put over here. This table of values will be very important because this is a long way of determining how you determine the slope from which you can determine the equation. And doing this way, you can see exactly how the concept of limit plays out. This, as I told you earlier, is a long way of doing it. Derivatives are the quick way of doing it, and I'll show you the quick way at the very end. So let's start. You always want to take values on both sides of the point you have. This is a point I have, 5, 2. I want to use x values which are on the right side, and I want to use x values which are on the left side. But as I was showing you, as you bring points closer to your point that you have, you change the direction of the secant line. So that's what I'm going to do. I'm going to put some points that will be getting close and close to 5 from both the right side and the left side. I'm just going to put a 5 over here because this is a point I have. I don't want to use this point at all because what happens if you put 5? Look over here. If you put 5 here in the slope formula, you'll get a 5 minus 5 and you'll get something divided by 0 and it'll become undefined. You don't want to use 5 because you'll make your entire slope undefined by virtue of having a 0 in the denominator. But I want to work from the right side and the left side coming close to 5. A value that I will start out with not too far away is number 6 over here. Like 6 would be right here, x1 over here. Then I want to, let's make this a 7 just for the effect of having a good delta x over here. The next number I want to bring in is a 6 because now I'm trying to make these right-sided values close and close to 5. And I'm going to need a calculator for this process over here. The next number I want to do to bring it closer to a 5 is I'm going to put a 5.5. Remember, I'm getting closer to 5. Then I'll put a 5.1. Then I'll put a 5.001. You see this? I've brought values further away from 5 but towards 5 in the direction from right up to that point. Now I'm going to do the exact same thing but from the left side but coming close to 5. Here on the bottom I want to start with a 3. You can put whatever values you want. I'm putting a 3. My next value I'll put is a 4 because I want to try to get close to 5. Then I'm going to put a 4.5. I'll put a 4.1 and here I'm going to make this little erase mark over here just so I can squeeze in another value. I'm going to put a 4.001. You see on both sides I've come close to a 5 but I'll never use the number 5. Now let's look at delta x. Delta x is always x2 minus x1. What you are assuming or using minus what you have. If I'm using 7, my change in x is always with reference to 5, right? 7 minus 5 is a 2. 6 minus 5 is a 1. 5.5 minus 5 is a 0.5, and nothing wrong with using decimals. 5.1 minus 5, the delta change in x is 0.1. 5.001 minus 5 is a 0.001. Alright, let's work down here. A 3 minus 5, I'm getting a minus 2. Nothing wrong with having a minus here because we're working from the other direction. A 4 minus 5, a minus 1. Remember, we're looking here at the delta x. As we're getting closer and closer, these values here, the change in x is getting closer to 0. Why is the delta x getting closer and closer to 0? Because at the very end, if you were to actually use 5, you'll have 5 minus the original 5, it would become 0. It would 0 out. We don't want to 0 out because we'll end up with a 0 in the denominator. Let's use a 4.5. 4.5 minus 5 is a minus 0.5. 4.1 minus 5, what is that going to be? Actually, I have a little bit of mistake over here, but that's alright. Remember, I'm supposed to get closer and closer to 5. This should have been a 4.9 because I'm trying to get closer to 5. This should have been a 4.999, right? Closer to 5. A silly mistake, but that's alright. I was able to pick up on it. 4.9 minus 5 is a minus 0.1. 4.999 minus 5 would be, you can imagine, minus 0.001. Let me check that out. 4.999 minus 5 is a minus 0.001. Now this is the part where we need a calculator to actually calculate the slopes of these are all secant lines, not tangent lines. We are aiming towards a tangent line, but we're not there yet. This right here, a coincident point on top of original point would give you the tangent right over here. But so long as you're not on your original point 5 comma 2, right, you'll always be dealing with a secant, though the secant lines will be getting ever so close from both sides onto your original point. But again, these are slopes of all the secant lines. Eventually we'll use that limit to get the slope of the tangent line. So this is how we're going to do it. We're going to use this formula right over here. We're going to plug in our x value in place of x's over here, and then we're going to actually calculate the slope. So let's start with number 7. When I put 7 right here on the top, I do a 7 minus 1 and I square root it because I have a square root over here. Then I minus 2 from it. And then I divide it by my delta x. This right here is always delta x. You don't have to start doing 7 minus 5. You already have your delta x over here already shown. Remember, x2 minus x1 is delta x. Divide this by 2. And what do I get? I got a little error over here on the calculator. It was 7 minus 1 square root minus 2 divided by delta x, which is 0.2247. The only reason why I got an error is I hit that one function twice and it doubled it instead. Let's do the next part. Let's put 6 over here in place of this right here, x, and calculate for the slope using the 6 value. So I'll do 6 minus 1 and I'll square root it using here, then I'll minus 2 and I'll divide it by my delta x. I do that, changing x is 1. My answer here is 0.23606. Now you'll be seeing a trend over here in these numbers. I'll present down here and the numbers here on the top. But we're not going to see that trend until we actually plug in this entire table of values. Let's look at the next number, 5.5. We will do 5.5 minus 1. Remember, I'm putting all the x values here in the slope formula here in place of x. So 5.5 minus 1, I'll square root that, I'll minus 2 and I'll divide that by change in x, which is part of the formula, and I get a 0.24264. Let's do 5.1. 5.1 minus 1 right here, square root it, minus 2 and divide it by 0.1 because that's my change in x. Look what I get. I get a 0.24845. You can take it to however many decimal places I want. Let's use 5.001. 5.001 in this formula right here, minus 1, square root it, minus 2 and divide it by your change in x, 0.001. I get a 0.24998. You see what's happening? We're getting ever so close to some number. That number right here will represent the slope of your tangent line. But let's work now from this bottom up towards 5. Let's use the number 3. We'll put 3 right over here as the x values and we'll solve for the slope. We'll do 3 minus 1, we'll square root it, minus 2, and we'll divide it by your change in x, which is a minus. See, I'm getting a minus number here. I'll divide by this minus and we'll get the positive answers. So we'll divide this by minus 2 and here I'm getting a 0.2928. Remember, these are all representing the slope of a secant line. We're getting close to our tangent, but we're still on a secant line. Let's use number 4. 4 minus 1 square root, we're using this formula right here, divided by change in x, which is a minus 1. Look, I'm getting a 0.2679. I'll keep it to 4 decimal places. Here I've had 4 and 5, but let's keep it to 4 only. Let's use this 4.5 in this formula. 4.5 minus 1, we'll square root that, minus 2 from it, and we'll divide it by this minus 0.5, which is a change in x, and I get a 0.2583. Let's use 4.9, then we'll do one more value and then we'll be done with the table of values. But we're at 4.9 right here. 4.9 in this formula right here, minus 1, square root it, minus 2, and divided by the change in x, which is 0.1 minus, I get a 0.2515. This right here is a 5. Alright, 5. Last value, 4.999. We'll put 4.999 in this. 4.999 minus 1, square root that, minus 2. I get a pretty small negative answer when I divide that by this negative change in x. Divide that by 0.001 minus, I get a 0.2500, but I actually end up here as my fifth number. I get a 5, I get a 1. Who cares? It's fine. But look over here. As we move from values on the rightward side towards our point of interest, which is right here, 5 comma 2 is my point of interest. 5 is specifically the x value. As the x values move from my right direction, however far away, closer to the x original direction 5, you see how as the change in x, as the difference in x became closer and closer to 0, my slope became closer and closer to, it seems to have been 0.25. 1 over 4, like a quarter. Look over here on these lower values. As I move from the leftward side towards this original point, from smaller numbers towards 5, my change in x changed closer and closer to 0. Remember, you could have 0.000001. Eventually it will be zeroed out. But my slope of that instantaneous rate of change, actually the average rate of change, became closer and closer to an instantaneous rate of change. See how it's getting 0.25001? Very likely the next term would have been 0.25. And this right here, by using this elaborate process, gives us, via the use of limits and assumptions and estimations and the use of slope, secants and average rate of change, we get an instantaneous rate of change of 0.25, which is a 1 over 4. So allow me to erase this and show you how we can write this in terms of limits, because that limits will represent one of the definitions we need to present. We're going to present two limits, one from the right side, one limit from the left side. So check this out, limit as delta x. Why am I using delta x? Because we're emphasizing so much on delta x. As delta x approached 0, see, as delta x approached 0, or you can say as x value approached 5. Okay, as the x values approached 5 from the right. You see, we're looking here from the right side. From the right, what happened to the, well, we can say what happened to our slope. The average slope became an instantaneous rate of change. It approached 0.25, right? Our function, or slope, or rate of change, average rate of change, it approached 0.25. Let's look at the other limit from the leftward side. Limit as delta x approached 0, or let's just say as x values approached 5, but from the left. See, these are values which are approaching from the left side towards 5. What happened to m, the slope, the average rate of change, the function, the secant function, or the secant line? It became more and more closely approximated towards the tangent line. That is, the slope became more and more close to 0.25. That 0.25 over here represents our instantaneous rate of change. Instantaneous rate of change, IROC, instantaneous rate of change, which is the slope of a tangent line. So we have to actually answer this question. The question is, what exactly is the equation of the tangent line? Well, we now have a slope 1 over 4. All you have to do is put the values of y and x, and you have your x and y values, and we're determining the equation of a tangent line at 5 comma 2. 5 comma 2, here's my x value, here's my y value, and we have a slope. So y is equal to 1 over 4x plus b. If you are to put the values 5 and 2 over here, you can actually calculate b. Now, in the interest of space, I'm going to do some erasing over here so I can generate space to actually give you an answer over here of this equation. I'm going to have a y is equal to 1 over 4x plus b. I know my y value is a 2, and my 1 over 4 is going to multiply with the 5. So let's bring out a calculator. I have a 1 over 4, 1 divided by 4 multiplying with the x value of 5. I'll save that, and then I have a y value of 2. 2 minus that value, I get a 0.75. So my final equation is y is equal to x over 4 plus 3 over 4. That's my equation of the tangent at 0.5 comma 2. Y is equal to x over 4 at plus 3 over 4. So this line over here, the equation for this tangent line would be y is equal to x over 4 plus 3 over 4. It'll have a slope of 1 over 4, and you can see in the long way by using secants, as we're gradually changing the direction of secant towards that of a tangent line, we are changing the slope so much so that we could actually pick out what the actual slope would have been for the tangent line. It's a 1 over 4. So my equation is y is equal to x over 4 plus 3 over 4, the equation of the tangent line at 5 comma 2. And this slope will represent the instantaneous rate of change. If someone were to ask you for whatever model this data represents, what is the rate of change at 5 comma 2? The rate of change will be 0.25. 0.25 what are units divided by what are units. We don't know what x units represented. It could have been time. We don't know what y value represented. It could have been money. So it would be 0.25 like dollars per unit of time, or 0.25 what are exponential growth of bacteria per unit of time. So that's the concept of instantaneous rate of change. More useful than average rate of change. Now, as promised earlier, I'll show you how you could have done this all using derivatives. A very quick and easy technique. I'm going to erase everything over here except for this original question and this original function, and I'll show you how the derivatives work. You may not understand how it works because you may not know what derivatives are. But this is just to show you, if you never wanted to get into the theory or the long part behind it, this is your ticket out of this whole concept. In this part of the video, I want to show you derivatives. Not as a lesson or as anything else other than to show you how this whole topic question could have been answered perhaps in under a minute, rather than using a table of values, graph, and doing right and left side limits. Look at this. If you know how to do derivatives, all you have to do is take derivative of your function that you're given. The function is root, right here, square root of x minus 1. You use something called a chain rule. Don't worry about what any of this is, because you'll learn it in the future. You do derivatives, carry them down, you'll get 1 over 2 root u, and you'll get 1 over 2 root x minus 1. Again, don't worry about how I'm deriving any of this, but this is the concept of derivatives. Right over here, I've gotten my final derivative of this question. All I have to do is, you see this x value here of 5, all I have to do is plug 5 over here. What happens? 1 over 2 root 5 minus 1. What does this give me? 1 over 2 root 4, 1 over 4, right? If you calculate this out, you get 1 over 4, which is what? 0.25. Remember in the previous question, I calculated the instantaneous rate of change as 0.25. Well, here I have calculated the instantaneous rate of change at 0.25 in maybe under 20 seconds of this function over here. And you can do exact same thing of using y equals mx plus b. This is just to actually answer the question, the equation of the tangent line. You can plug this in here with your 5 comma 2 and get that same equation. Y was equal to x over 4 plus 3 over 4, and the question is done in under 30 seconds. Well, under 30 seconds, if you eliminate the count time of the talking, you can do it actually faster. So this right here is your cheat procedure. Cheat procedure involves derivatives. You've probably heard of derivatives. It's like the initial huge part of calculus is all derivatives. The whole concept of derivatives is to easily calculate tangent lines, the slopes of those tangent lines, because again, those slopes represent the instantaneous rate of change versus average rate of change. Secants are to do with average rate of change. Tangents are to do with instantaneous rate of change. You have two procedures. The long procedure where you use approximations and limits to get close to the number you are given. Work from the right side, work from the left side until you get a clear trend of where that limit is headed towards. That clear trend is represented by a number which will be your rate of change. Or you can use derivatives and do it the quick and easy way. If you want to use this, I don't know why I'm even calling it a cheat way. Maybe it is cheat, but there's nothing wrong with you all learning how to do derivatives first before you get into the theory of it, because once you can do the derivatives, you can always check to see if your answers are actually right. But again, there's nothing wrong with using derivatives to calculate instantaneous rate of changes. It's a quick, easy, a foolproof method. Well, I hope you all enjoyed this video. Maybe I might present a video in the near future with another example using a different type of function and a different set of points to determine an equation of another tangent line. Eventually we will have to present some more of those as we actually talk about derivatives. Remember, the concept of derivatives kind of skips the whole procedure or the process of learning why you have to do all of this. You just learn in a robotic manner how to do it, and once you know derivatives, any type of equation, it could be a hyperbolic, it could be a radical, it could be an exponential, it could be a logarithmic, you can determine using derivatives the instantaneous rate of change. The procedure before using approximations become a little more difficult as your equation form becomes difficult. But I hope you enjoyed this video. Please like, subscribe, share, and leave a comment. Have a great day. Thank you.